Welcome back. In this video we're going to take a look at a particular class of isomorphisms, and these are called automorphisms. They are basically isomorphisms from a group back onto itself again, and it turns out that these have a lot of interesting properties that we'll have a bit of an explore of in this video. Right, so here's the definition, and it's just what I just said. An automorphism is just an isomorphism that's from a group onto itself. So we know how to test for isomorphisms already, and testing for an automorphism is exactly the same. The only difference is that the group is itself on both ends of it. So here's for one that we won't bother proving. So we'll look at a map, for example, from the complex numbers onto the complex numbers under addition, and an example automorphism would be phi of a plus bi is equal to phi of a minus bi. So you do the normal thing, you'd show that it's one-to-one onto and operation preserving, and then that would automatically be an automorphism. Okay, now there's a special class of automorphisms that we're going to consider for a moment, and it's the so-called inner automorphisms, and these apply to each element of a group. So in this case, we have a group G with some element A, and for each element in that group A, we can define a mapping phi A of x, which is equal to AX A inverse for any x in our group. Okay, so we get a different one of these mappings for each x that we choose, and these mappings form inner automorphisms. Okay, again, I'm not going to prove that this thing is an automorphism. I'll let you guys do that for yourselves. We did a very similar example with matrices earlier, so it's not a difficult thing to show. But these are inner automorphisms. So let's look at an inner automorphism of a group that we know. So I'm going to look at D4. So we'll take the inner automorphism of D4 induced by R90. Okay, it's a bit of a mouthful to get your tongue around. So the inner automorphism of D4 induced by R90, just to see how this formula actually applies. So phi R90 of x is just going to equal x R90 x inverse. So I can make up a table of these. So we know in D4 we have the following elements: R0, R90, R180, R270, H, V, D, D prime. So this can be x, and here we're going to have phi R90 of x. Okay, so that is equal to x times R90 times x inverse. So in this case here, I'm going to have R0 times R90 times R0 inverse is just equal to, sorry, R0, not R90. Getting this back to front. I've got all my notations back to front. My apologies. Let's just back that train up a little bit. So phi R90 of x is actually equal to R90 x R90 inverse. Got myself back to front there. Right, that makes more sense. I was trying to figure out why that was not working. So if we go back to here and we put in R90 into our formula, so phi R90 of R0 is just going to be R90 times R0 times R90 inverse, and that will clearly, if you just multiply that all out, we know that R90 inverse is R270, so that overall gives us R0. And similarly, for R90 we get R90 times R90 times R90 inverse, and that just gives us R90. And in fact, you can see that for all of the rotations, because they commute, the inverse just cancels out the R90, and we just get left with what the element itself is. However, because rotations, or R90 does not commute with the reflections, we do actually get different things here. So I'm going to do R90 times H times R90 inverse. Put that together, and you actually get V, a vertical reflection. Again, I'm just consulting a Cayley table for D4. You might want to have one handy. So phi of V is R90 V R90 inverse, and that's equal to H. Continuing on the same way, you find you get D prime for D and D for D prime. Okay, so that is what the inner automorphism of D4 induced by R90, that's what it looks like as applied to each of the 8 elements of D4. And we could make one of these inner automorphisms for each element of our group, and that'll all be slightly different. Okay, a little bit of notation. We'd call AUT, aut, of G, is the set of all automorphisms of G. And also we have in, short for inner, of G is the set of all inner automorphisms of G. And actually it turns out that both of these sets are groups. So we can state that as a theorem, which again, I'm not going to prove. I'll leave it to you guys to prove. But our theorem is that the automorphism aut G, the set of all automorphisms, forms a group under function composition, as does the set of inner automorphisms. Groups under function composition. Okay, so these are called the automorphism group of G and the inner automorphism group of G. So what we're going to do is we're going to look at an example and we're going to try and find out what the automorphism group of Z10 looks like. So we're going to take Z10 and we're going to try and examine all of the automorphisms of Z10 and see if we can get some sense of what this automorphism group actually looks like. So the way we're going to attack this is we're going to set ourselves up a generic automorphism of Z10. So I'm just going to say let alpha be an automorphism of Z10. So we could say that as a shorthand way of saying that would be let alpha be an element of the automorphism group of Z10. Apologies. Okay, so we want to know what we can find out about alpha, given that we know alpha is an automorphism. And this is where understanding how isomorphisms work is really useful, and we can consult our list of properties. Because we know that alpha of 1, for example, is going to give us a lot of information. We know everything. Why is that? Because Z10 is a cyclic group, and 1 is a generator of Z10, and therefore alpha of 1 must be a generator of Z10 also. Because alpha of k, just using operation preservation, is equal to alpha of 1 plus 1 plus 1 plus etc. k times, has got to be equal to k times alpha of 1 by operation preservation. So we actually know a heck of a lot right from the start. We know that alpha is an automorphism. Once we know alpha of 1, we know that 1 is a generator. So if I take k from Z10 here, I can express my k as a number of 1s, where 1 was our generator. And then because of operation preservation, they can be combined after alpha also, so that has to also be equal to k times alpha of 1. Okay, so let's express this in terms of element orders. We know that the order of 1 equals 10. And again, property of elements under isomorphisms is that the order of alpha of 1 must be 10 also. It's also equal to 10. Alright, therefore, we can find alpha of 1 by looking at elements that have order 10 in Z10, and these are just the elements that are relatively prime to 10. Okay, so I guess the question is, are these things automorphisms or not? So we've got 4 different possibilities for alpha of 1. That corresponds to 4 potential different automorphisms. So we'll define these mappings by alpha 1, by alpha 1, alpha 3, alpha 7, and alpha 9. So just to remind ourselves what the mapping is, we get alpha, e.g. alpha 3 of x is equal to 3x. Okay, so it's k times alpha of 1. Alpha of 1 for alpha 3 was equal to 3. So alpha 3 of k or x is equal to 3x. So we better test that these are actually automorphisms. Or isomorphisms, if you like. Are these isomorphisms or automorphisms? Well, alpha 1 is just the identity mapping, so yes, it definitely is. Let's look, for example, at alpha 3. If we do one-to-oneness, we'd have, if we took alpha 3 of x equals alpha 3 of y, this would mean 3x equals 3y mod 10, which would in turn imply that x is equal to y mod 10. So alpha 3 is definitely 1-to-1. Now alpha 3 of 1 is equal to 3, which is a generator of Z10. So alpha 3 is therefore onto. This is because I can get every element of Z10 as some multiple of 3, and that k, the multiple of 3 that you take, the thing that multiplies 3 is the k that goes before the alpha into it to make the element that we want. So it's definitely onto, and operation preservation is pretty easy to show as well. This is onto. Operation preservation, we have alpha 3 of a plus b is equal to 3a plus b mod 10, which is equal to 3a plus 3b mod 10, I'm just omitting that, which is equal to alpha 3 of a plus alpha 3 of b. So yes, we indeed do have that these things are all isomorphisms of Z10 to itself, i.e. they're all automorphisms. So we had 4 possible candidates. The same working applies for each of these, and so these 4 are indeed automorphisms. Now finally, we've got to work out, we're claiming that the automorphisms form a group. So what does the group structure look like? Well, what is alpha 3 composed with alpha 3, for example? So alpha 3 times alpha 3 of x, well, that's equal to 3 times 3x is equal to 9x, which equals alpha 9 of x. So actually, the subscripts multiply here. Let's try that again. Alpha 3 times alpha 7 of x is equal to 3 times 7 times x equals 21x mod 10, so that equals x equals alpha 1 of x. So you can see that my multiplications here are just multiplications mod 10. So the mod 10 has sort of been carried through here. So actually what we've got is we've got the subscripts multiply mod 10, and the elements are 1, 3, 7, and 9. These are all the elements that are relatively prime to 10. Therefore, we're just pretty much working in U of 10 here. We've just got some extra alphas decorating them, but it's the same structure. So this looks like U of 10. A group operation is multiplication mod n on the subscripts, and our 4 elements do correspond to the 4 elements of U of 10 as subscripts. So that leads us on to state that this is a theorem, which we can prove using the same method we've just used to attack Z10. So theorem 6.5 says that the automorphism group of Zn, whoop, losing control of my computer, try that again, is isomorphic in fact to U of n. Okay, so we're going to prove this essentially using the same ideas and the insight we kind of gleaned from our example, just to kind of formalize what we've just talked about and to make this into a proper proof. So we'll just sort of make the same note that we made before. Any automorphism of Zm is determined by alpha of 1, for the same reason that once we knew alpha of 1 over here, we kind of had the whole thing, and that gave us the whole transformation. And we also know that alpha of 1 is a member of U of n, because it has to generate Zn, therefore it has to be relatively prime to n, therefore it's got to be a member of U of n. Okay, now to show that the automorphism group and U of n are isomorphic, we need a map between the automorphism group of Zn and U of n. So let T be this mapping. So consider our map T from the automorphism group of Zn to Un. So this is going to be the mapping that we're going to check is actually an isomorphism, defined by T takes alpha, okay, our automorphism from the automorphism group, and maps it onto the subscript that we had there. Again, apologies for the computer going wild. Okay, and the subscript we can just get by taking alpha of 1. So there is our candidate mapping between the two groups. Now we just need to show that it's an isomorphism. So 1 to 1. So for this one, we need to show that, assume that T maps two different automorphisms to the same thing. Then alpha of 1 equals beta of 1. So we've showed that alpha of 1 and beta of 1 are the same thing. We want to show that the whole mapping, the whole automorphism alpha and beta are the same thing. So we need to check that they actually give the same value for all values of k. Then alpha of k is equal to k times alpha of 1. Here's how we can link the whole transformation together, which is also equal to k times beta of 1, which equals beta of k for any k in Zn. Hence, alpha is equal to beta. Alright, then we need to show that our mapping is onto. Just pause this while I sort my computer out. Be right back. So what does this mean here? This means that no matter what alpha of 1 I choose, I can find a corresponding map alpha. So my alpha of 1 is going to be a member of U of n, so let R be an arbitrary element of U of n. I need to make sure there's an automorphism that corresponds to it. So we will we'll define our automorphism, or consider an alpha that maps Zn onto Zn, defined by alpha of S is equal to S times R. Okay, so this is just, the R is taking the role of the 1, 3, 7, and 9 for my Z10 example. And I'm defining the mapping pretty much in the same way. Alpha of S is equal to S times this R, times this alpha of 1, if you like. We can show that alpha is an automorphism. Then T of alpha, let's show that this alpha we've produced is going to give us the R that we want. Is equal to alpha of 1 equals R, and therefore we have an automorphism that gives us the R that we're after. And finally, we need to show that it's operation preserving. So to show it's operation preserving, we choose two mappings in our automorphism group. And we're now going to show that it gives us what we want if we compose them together. So if I take T of alpha beta, that is going to give me alpha beta of 1. Now remember they're multiplied by function composition, so it'll be alpha of beta of 1, which by how these things are defined is beta of 1 times alpha of 1, which in turn equals alpha of 1 times beta of 1, because multiplication of numbers is commutes, which is T of alpha times T of beta as required. So we've now shown that our T is 1-to-1 onto an operation preserving, therefore it is an isomorphism, and therefore our automorphism group of Zn is automatically isomorphic to U of n. Okay, so this links the Zn and U of n groups together in quite a nice way. So I'm going to do one more example before we end the video. We're just going to look at the inner automorphism group of D4 now. So what we want to do is we want to calculate or figure out what all of the inner automorphisms of D4 are. Now we did phi R90 in previously. We looked at what that would look like. Now we want to consider what all of these things are. We want all of them. In all inner automorphisms. Okay, so our possibilities. We know that we get one inner automorphism per element, so we should have these as our collection of possible inner automorphisms. Okay, one for each of the elements of our set D4. However, it may be that two of these or some number of these are actually the same transformation. So we don't know that this is our full set. This might be overcounting them. So we're going to take use, remember that these are defined by the element times x times the element inverse. So when things commute is when things potentially are going to cancel out. So we're going to remember the center of D4. We're going to remember that that was equal to R0 and R180, and we'll see why this is important in a second. Okay, center, remember the center is the elements that commute with every single thing in the group. So if we keep that in mind, and we look at, for example, phi 180, that's equal to R180 times x times R180 inverse. But remember, R180 commutes with everything in the group. So that equals x R180 inverse. This should be of x, sorry. Just equals x, which in turn equals phi R0 of x. So here's a start. Phi 180 and phi of R0 are actually the same thing. Should be phi of R180. So we've already got rid of one of our possibilities. We can do this similarly. Let's see if we can actually do this somewhere else as well. So let's say phi of R270 of x. Let's look at that one and see if we can make it into something else by making use of this center information again. R270 of x is equal to R270 times x times R270 inverse. And now we're going to introduce the center R180, the element from the center R180 into this by making it R90 R180 x R180 inverse R90 inverse. You can see that's the same thing. And we know that this term here is just x, so that's R90 x R90 inverse, which equals phi R90 of x. So, actually, phi of the inner automorphism induced by R270 is the same as that induced by R90. Similarly, H is equal to V times R180. So phi H equals phi V. For exactly the same reason, you can do the full working if you like. And D is equal to D prime times R180. So the phi D is equal to phi D prime. So actually we only have 4, and I'll leave verifying that these are distinct as an exercise. Verify that phi of R0, phi R90, phi H, and phi D are distinct, but they are. And so our inner automorphism group of D4 is that set there. So I think that's about enough for one video, so we will see you next time. Have a good one.